Hi folks, welcome to 8.4 polar graphs. And so in this video, we're going to take a look at what it means to graph in a polar form. And we're going to go ahead and get started with what we know. So what do we know? Well, at this point, hopefully we've got quite a few functions that we know what their shapes are kind of right off the bat, all right? So if we start with our y equals x, hopefully we know that is just a straight line that goes to the origin, has a slope of 1. Y equals x squared, we know is a parabola, has its vertex at the origin, and has some special points 1, 1, 2, 4, 3, 9. We know that y equals e to the x is an exponential growth function, and that there is actually a horizontal asymptote associated with the e to the x graph. We know that e to the x and natural log x are inverse functions, and so our graph for e to ln x kind of looks like a reflection of the e to the x graph. But that one, instead of having a horizontal asymptote, actually has a vertical asymptote. All right, more recently, we've been talking about sine and cosine. And so hopefully we know that our sine and cosine, if we were to draw an XY grid here, sine looks something like this, and it is an odd function. Whereas cosine looks something like this, and it is an even function, okay? So doing a quick check on the parent functions that we know so far, and these tend to be the ones that come up more frequently, okay? All right, so what's new? Well, we're going to take a look at graphs that have not x and y, but r's and thetas, okay? And so we've got some r's, we've got some thetas, and by the end of this lesson, we're going to know what these graphs look like, okay? Now, before we do that, a couple things I want to highlight here. All of our a's, those represent numbers, regular numbers. And all of our b's also represent numbers. And all of our n's also represent numbers. All right, so A, B, and N, those are all real numbers that we're looking at here, okay? All right, so in this video, we're gonna focus mostly on circles, all right? And then in each of the following videos, we'll focus on a different shape. All right, so what do equations of circles look like when we're looking at them in polar form? So if you were to go on Desmos and go on polar form and graph r equals some number a, okay? In fact, I'll go to my Desmos right now, show you how to do that. So we're going to go to our Desmos. And we're going to be in polar form. So I'm going to go up to this wrench in the top right-hand corner. And the grid I'm going to choose is the one with the circles. Okay, that's how we get into polar form. All right, so I'm going to type in r equals, and then I'm going to type in the letter a. Okay, r equals a. Let's pick a number for that, actually. Let's go r equals 5, okay? If I say r equals 5, looks like I have a circle, all right? It is centered at the origin, and it has a radius of 5. Well, what happens if I change that? Maybe I change it to 1. Now, if I zoom in here, all right, I've got a circle that has a radius of 1. I don't know why that keeps changing on me. I have a circle with a radius of 1, and it's centered at the origin. And what happens if I move this all the way up to 3? Well, now I've got a circle that's centered at the origin and has a radius of 3. Okay. So let's go back to our notes and write that down. That if we were to look at the equation r equals a, all right, let's draw ourselves a circle here. We'll move that over a bit to make it perfectly centered. But this would be the graph. And in particular, the A would tell us the radius. So radius, well, let's just write A. Okay. So whatever A is, if I plug that in, I'm going to get the radius of that circle. All right. Now, we're going to go back to Desmos, and we're going to graph r equals a cosine theta, and then we're going to graph r equals a sine theta and take a look at those. Okay, so let's go back to Desmos and go here. R equals a, oops, a cosine theta. I'm going to add a slider for a. Okay. So this is one of the nice things about Desmos. So I can say, let's just focus on what happens if we have whole numbers here. Okay. But if I graph this, I can, or if I change the A, I can see that the circle gets bigger. All right. So let's zoom in so we can see if I get all the way out to 8, now I have a circle that goes from 0 to 8. And if I were to go all the way out to 10, I would have a circle that goes from 0 to 10. Okay, so the A seems to control how big the circle's going, all right? But you'll notice that our circle's not centered at the origin anymore, and that's okay, all right? So it turns out when we have the cosine there, that our circle is going to be to the right of the graph. Now, you might be asking, Judy, what about if we change a to a negative number? And that would be a great question to ask. So let's see. We're going to click this slider. We're going to go across. Oh, when a is negative, now my circle's on the left-hand side. Okay. So if a is positive, we have a circle on the right-hand side. If a is negative, we have a circle on the left-hand side. And now our A here is no longer our radius, but it's actually our diameter, okay? Now, I wonder, let's change this back to 1 for a moment and zoom in. I wonder what happens if I change this sine to cosine, all right? So let's type that in. R equals a sine theta. I'm going to click on that, turn the cosine graph off, and I notice that as soon as I change sine to cosine, right, sine was on the right, now cosine is actually above. It is above the x-axis, okay? Now, I wonder, if I change A and make it bigger, is my diameter still going to change? Sure is. This has a diameter of 5, diameter of 6, diameter of 3, okay? And I wonder what's going to happen when I make a negative. So take a moment, think about that. What do you think is going to happen? And now let's see. Yeah, it goes down to the bottom, okay? So when we're thinking about sine and cosine, it changes a few things in our picture, all right? So let's go back to our notes and write that information down. All right, so if we have r equals a cosine theta, all right, we end up with a circle on the right, but this distance is if we have a positive a, okay? Now, on the other hand, if we happen to have a negative a, let's change that from positive a to negative a, we end up with a circle on the left-hand side, okay? And what happens if we have our, what happens if we have our sine instead of cosine? Well, like we saw in Desmos, we end up with a circle that is above, right? So this whole distance is our a value. And if we think about what happens when a is negative, well, that circle is now on the bottom of the y-axis, okay? So this is sort of a visual of what it looks like with those changes, but let's write down some notes for ourselves, okay? So I might say for r equals a, that we have the center at the origin. Okay, that's probably one important thing. And also a is the radius. Okay, so we have a circle, center at the origin, and a is the radius. All right, well, what about this middle graph? What might we write about that? Well, we might have a circle to the right of the y-axis for positive a. And then we can copy and paste this sentence, but change it for negative a, right? If we don't want to go to the right, if we want to the left, that's going to be for negative a, all right? And one last thing to write down, a is the diameter, right? So a is not the radius, but a is the diameter. All right, now, how would we take this information and modify it to write for the third picture? Okay, so let's actually duplicate and modify. So we don't have a circle to the right or the left, so we'll get rid of those. And it's not the y-axis, okay? But if we have a circle above, oh, too many words now, a circle above the x-axis for a positive a, and a circle below the x-axis for negative a, right? But that last sentence, a is the diameter, that doesn't change, all right? So now when we look at equations like this, we want to be able to look at it and say, oh, I know exactly what that's going to look like, okay? So let's practice that a little bit in some examples. All right, example 1, we've got r equals 5 cosine theta. All right, let's predict. Our radius for this should not be 5, but our radius equals 5 divided by 2, and we can think about that as 2.5, but I prefer really to see it as 5 halves, okay? Now our axis of symmetry. Well, let's go back and take a look at our picture for a moment. Our axis of symmetry for these are the x-axis when we have cosine, okay? And that might be something we remember. Cosine is the x values on the unit circle, so the axis of symmetry here is actually the x-axis, okay? So axis of symmetry is going to be the x-axis, all right? So I can already draw a picture. So we're going to go ahead, before we draw our picture, we're actually going to plot a few points and see, okay? Because let's say we forget. Well, we still want to be able to figure this out if we use a table, okay? So let's start with theta equals 0. All right, if we put 0 into the equation 5 cosine theta, let's see, cosine of 0 is 1, 5 times 1 is 5, so the r value is 5, but the way we write the point is r comma theta, so 5 comma 0. And I'm going to do the same thing over here, pi over 6, pi over 4, pi over 3, and pi over 2. So I'm going to pick the nice values on the first quadrant of the unit circle, okay? And now if I put those values into the equation, let's see, 5 cosine of pi over 6 is going to give us about 4.33. So we know 4.33 comma pi over 6 is a point. All right, let's try it with pi over 4. So 5 cosine of pi over 4 will give us about 3.54. So we get 3.54 comma pi over 4, all right? And if we plug in pi over 3, we should get 2.5, and that's 2.5 comma pi over 3. And last but not least, if I plug in pi over 2, I'm going to get 0, and that's 0 comma pi over 2. All right, so let's plot these points and see what we get, okay? So 0 comma 5, or 5 comma 0, excuse me. I'm going to go to pi over 6, and I'm going to go out 4.33. I'm going to go to pi over 4, and I'm going to go out about 3.5. I'm going to go to pi over 3 and go out 2.5. And I'm going to go to pi over 2 and go out 0. Okay. Now, if I zoom in, these are not perfectly plotted points, but I can start to see that I have the top half, the top half of a circle. Okay, now because we know that this is symmetric about the x-axis, really I know that the bottom part also looks like this, which is going to give me a circle. Okay, so knowing now that I've got my circle, I'm going to go ahead and try to draw one and see if the technology will help us out. All right, not bad. All right, so we've got a circle here, and that matches up with our predictions. Okay. All right, let's try one more example. R equals -4 sine theta. Okay, so I know the radius is going to be 4 over 2, which is 2. And the axis of symmetry is going to be symmetric about the y-axis. And this negative means it's going to be below the x-axis. Okay, so being able to look at the equation and kind of see what patterns there are here, I think that's going to be really important. Okay, now, again, I can go ahead and plot some points using the calculator and to figure those out. But this time I'm going to suggest that we actually choose some nice values. Okay, so what I mean by that is if I put in 0 into the equation, -4 times sine of 0 is going to give me 0. Okay. But let's see, sine of 30 degrees or pi over 6 is 1/2. So I'm actually going to choose pi over 6. I know that sine of pi over 6 is 1/2, so -4 times 1/2 is -2. So -2 comma pi over 6 is actually a point on there, okay? Now, if I plug in pi over 3 and pi over 4, I'm not going to get quote unquote nice values. So I'm going to skip to pi over 2. When I plug in pi over 2, I'm going to get 1 for the x value. 1 times -4 gives me -4. All right, so let's plot those points so far and see what we get. We get 0, 0. We get pi over 6, but -2. That's here. And I get -4 comma pi over 2, 1, 2, 3, 4. Okay. Now this is symmetric about the y-axis. So I know there's going to be a point right here. Okay. And now, even though this looks kind of like a diamond-y situation, right? Because it's of the form a sine theta, I know that it's actually going to be a circle. Okay, so let's use our technology to help us out here. All right, so here we go. We've got our second example. We've got a circle that is below the x-axis, has an axis of symmetry of the y-axis, and it's got a radius of 2. Okay, so on an exam or a quiz, I do expect that we're able to predict things without graphing on Desmos, right? So that can be something we expect on an exam, but also knowing that we can use our nice numbers and how we choose those as part of the process, right? How can we use some of those nice numbers to help us get an idea of the sketch? All right, folks, that's it for the first video. Come on back for the second part.